From Monday to Tuesday, we improved our rectangular method. How? What was the difference from Monday to Tuesday that made it better? Yeah, how did we get more accuracy? We switched to MRAM, right? We went from LRAM, and we had RRAM on Monday. Tuesday, we switched to MRAM, and it gave us more accuracy. In MRAM itself, how can you get more accuracy? Having more subintervals. More rectangles means more accuracy, okay? But there's a shape that's even better, okay? So that I've already told you what it is, but let's see how this is better. Okay, so I want you to look. This is not for anything for you to write on. This is just a visual. Here's an MRAM picture. And this MRAM is definitely better than an LRAM or an RRAM, but you can see there are still lots of places where either it underestimates, we've got lots of yellow that is missing area, which we would want. But then there's also places, I'll make blue, that are quite a bit over. So we don't have complete and full accuracy yet, okay? So if we take the same exact shape with the same exact subdivisions, and if you go to your next slide, if we switch it to trapezoids, in most cases, the trapezoid is a much closer approximation, and we have a lot less error, with one glaring exception. There is one particular section that the trapezoid is really a terrible approximation. Which one is that? Okay, the very last one. Yeah, that very last one is really a terrible, because that section itself has both a combination of increasing and decreasing. So how would we make that better? Well, we'd want to take that section and we'd want to split it again in half to improve that. Because if we split it and we did a trapezoid and did a trapezoid here and here like this, that's going to eliminate that whole chunk, a big chunk of the area that's an overestimate. But for the most part, trap is a better estimate. And so that's why on Monday, and again yesterday, we reviewed the formula for a trapezoidal area. Okay, we know that rectangles are simply base times height. Trapezoid still has a base, but instead of having one height, it has two. It has a height on the left and a height on the right. And so what do we do with those? Average them, right? Add them together and divide by 2. Okay? All right, here's another example. Now this is a little bit new. What's on here besides having a trapezoidal shape? Oh, do you see there's one rectangle on here? Where do you see it? What color?
Blue.
Okay, blue. So why is that a rectangular shape?
Both sides are
The two sides are the same. Okay, so is a rectangle a form of a trapezoid? Yes. Okay, it's a trapezoid that has two of the same sides. Is every rectangle a trapezoid? Is every trapezoid a rectangle? No. All right, but what else is different here that you haven't seen before? Oh, there is a triangle. Okay, so why do we have two triangles? Is a triangle a trapezoid? It is. Okay. Triangle is a trapezoid. It's just what's one of the sides? One of the sides is 0. Okay. And then we also have negative ones, right? We've never seen that before, that we have things that are negative. So if you have things that are below the x-axis, their area is negative, not positive. Okay, so you're going to have negative area. So the answer would turn out to be negative something instead of positive something. All right, here we go. Trapezoids are found the following way. 1/2 base and then the 2 heights. Or you could also write that as base, and then you could put the height on the left plus the height on the right divided by 2. Those are exactly the same thing. Whether you do divided by 2 on the inside or you put multiplied by 1/2 on the outside, they're the exact same. Okay, it's totally up to you. And so what we would do then is instead of finding R1 plus R2 plus R3, etc., or M1 for the midpoint plus M2 plus M3, we're now just finding T1 plus T2 plus T3. We're finding all the trapezoids individually. Any questions on the method? All right, so you've seen this graph now. It's our third day in the row of doing the same graph. The first day we did it with LRAM and RRAM. And the second day we did it with MRAM. Today we're going to do it with traps. So go ahead. We're going to do 6 traps. So go ahead and subdivide this. In order to do 6 traps, we need 7 data points. Okay, and then do your best to draw the top of each trapezoid. All right. You can maybe see it best on the first 2. Okay, if you look at mine, how my tops end up, is every trapezoid, are the trapezoids larger or smaller than the actual area? They're all larger, okay? Even on the increasing and the decreasing area. So here is a section, you look at these first 2 sections. One is a decreasing section, one is an increasing section, but they are both larger trapezoids than the other. So it doesn't have anything to do with increasing or decreasing. It has to do with concavity. What kind of concavity does this have? This is concave up. Concave up means the trapezoids will be larger. Concave down means the trapezoids will be smaller. Okay, this is an entirely concave up section, and so all of the trapezoids will be slightly too big. So our overall is going to be an overestimate by a little bit. Okay, let's find our T1, T2, T3, T4, T5, T6. So here's T1. What is its base? Okay, so I'm going to do trap over here. Its base is 0.5. And what are the 2 heights on either side according to the table? 3 and 2.75. So then I'm going to have 3 plus 2.75 divided by 2. I can write it like that. Or if you prefer, bless you, if you don't like the divided by 2, you could put 1/2 times 0.5 on the outside and then just leave the 3 and the 2.75 by themselves. 3 plus. So it's your preference on how you like that. But every trapezoid then, and T2, is going to still have a base of 0.5, and it's still going to have a 1/2 in the front. But its 2 heights are 2.75 and 3. And then the third trapezoid, it's going to have a 0.5 for its base. It'll have the 1/2, and its 2 heights will be 3 plus 3.75. And then you're just going to proceed all the way down through all of the different trapezoids. So you'll do that for trap 4, trap 5, and trap 6. So all of them are going to have a 1/2 and an 0.5 in the front, which will be common. And then we'll have 3.75 plus the next one, which is 5. And the next one will have 5 plus the next one, which is 6.75. And then we'll have 6.75 times the last one, which is 9. So the fastest way to use your calculator is to add up all of those things in parentheses, I think, because they all have the 1/2 in common and they all have the 0.5 in common. So what I would do is I would add up all of these first. And I'd come up with the total of adding. So let me see. Okay, I'm interested to hear what somebody gets because I got an answer. I just want to make sure I didn't type something wrong. Anybody get anything? I have a 54.5. Anybody get something different? I got something a little different. I may have made a mistake. So did anybody get anything different than 54.5? All right, so I don't know what I did wrong then.
She hasn't done the multiplication yet. She just added it.
Just adding it. All right, then what do? Then you take your 54.5 and you multiply it by 0.5 and you multiply it by half. Okay? And so the total for the trap, when you do 1/2 times 0.5 times 54.5, 1.25, what, 13.65. Oops. Wow, that's really close to, I don't know if you remember over the days, when we did LRAM, we got 12 something. When we did RRAM, we got 15 something. When we did MRAM, I think we got 13.25 or something like that. And now we have TRAP, which is our closest approximation yet. All right, how can you get even better than TRAP? This is a TRAP 6. How can you get better than TRAP 6? Sure, TRAP 12, TRAP 24, TRAP whatever, the more traps you have. But no matter how many traps you have, ultimately it will always be too big. Even by a little bit, because of the concavity. It's the concavity for trap. So I need you to keep that clear. For RAM, it's whether it's increasing or decreasing. For trap, it's the kind of concavity that you have. All right, so on the next slide, would you put that down? Concavity determines the accuracy of the estimate. Okay, concavity is the key. So if we have concave up, the implication is that trap will be too big. If we have concave down, the implication then is that all traps will be too small. Okay, trap too big versus trap too small, but it all has to do with concavity. All the RAMs have to do with increasing or decreasing. All the traps have to do with concavity. Okay, we can do trap without a graph. We can do trap with a table. So use trap to estimate the distance traveled by this car. So this has 6 values. So if I have 6 values, how many traps can I do? I can do 5. So I'm going to do a trap 5. My trap 5 is going to be 1/2 of the base plus the different heights. Height on the left plus height on the right. All right, so what is the first base between the interval of times?
7.
Okay, 1/2 times 7. And then the 2 heights I'm going to use, or the 2 values I'm going to use for this equation are 30 and 36. Okay, plus the next one will be 1/2 times, what's the next base interval? 5. So it's not always consistent. And then 36 is combined with 43. And the next one will be 1/2 times, and the next base interval of time will be 8. and then 43 is combined with the next value, which is 48. And then half times, so I've got 2 more to go. 6 is my base interval. So 48 combined with 44, and my last trap has a base interval of 4, and it takes the values of 44, combining it with the last value of 40. This one, there's no shortcut. You have to do each computation. So 1/2 of 7 times 30 plus 36, 1/2 of 5 times 36 plus 43, and you'll be evaluating, yeah.
But can you do like 7 times 36 plus 30 plus 36, and then just times 1/2 at the end?
Yes, yes. So you could do all of this part first. So 7 times 7 parentheses 30 plus 36 plus 5 parentheses 36 plus 43 plus 8 parentheses blank, and you could do all that and then just save the times 1/2 at the end. That would be the only way you could shorten this up. Sam, are you done with that already? You spaced out a minute. Okay.
There we go.
Where'd you get it?
I had mine in the fresh first.
2,407.
Okay, does anybody agree with that?
Yeah, before dividing.
Before dividing,
Oh,
okay.
yeah.
So still have to times by half, okay?
What?
So then we want to times by half, so that would be 1,236.5, and what would the units on that be? Looking up to the units.
Feet per second.
Not feet per second, feet. So what does that mean? Like, put that into context of the equation. What is that? 1,236.5 feet, what?
Down the road.
Okay?
Between 0 and 36.
That the car traveled, right? The car has gone 1,236.5 feet in how much time?
30 seconds.
In 30 seconds. Okay, in a 30-second amount of time it's gone that far. All right, so that's trap. You have a trap program which runs the exact same as your RAM programs do. All right, last thing. The last type of approximation we're just going to discuss, this is called a parabolic approximation. So a rectangle has a straight top connected to 2 equal sides. A trapezoid has also a linear top, straight top, connected to 2 unequal sides. A Simpson's parabola has 2 unequal sides connected by a curved parabola like this. And on the other side, you would have 2 unequal sides connected by a curved parabola. Simpson's has proven to be the most accurate, but it has a much more complex equation because finding the area of a parabola is this formula here. You got to take the height and divide it by 3, and then you have to do all this long stuff. You'll never have to do this by hand. Okay? You only ever have to use the calculator program for it. However, can you star this and circle it and highlight it and whatever? It only works for even subintervals. Okay? What's the power of a parabola? Squared. That means this only works when you have an even number of subintervals. Okay? If you try to do an odd number of subintervals, the calculator program will give you an answer that is wildly inappropriate. Okay? So let's try that a minute. Okay? So what I want you to do is the same equation we've been working on. Put that back in your calculator. And I want you to compare the difference between, if we're going from 0 to 3, and I want you to try what a simp 6 would look like, and then I want you to just check what a simp 7 would look like. Because here is an example of where more is not necessarily better. Okay, so simp 6 13.5.
9.89795. Yeah.
Simp 7, what did you get?
9.796.
Yeah, not like worse than the LRAM and RRAM we started with on the first day. Okay, but try Simp 8, because that's an even number. Or try Simp 12, or something like that.
I'm not getting those 5 at all.
Do you have the right equation in your Y1?
No.
Okay.
There it is. Figured out the issue. I forgot about that part.
Human error, not calculator error. Yeah.
I wish I could put it
Mhm. All right, so our last slide of this graphing thing that we're going to talk about. Which calculator program would be the best area? So let's just quick compare all the programs we have, just to put this all together. All right, I would like an LRAM 6, an RRAM 6, an MRAM 6, a TRAP 6, and then I remember the answer for Simp 6. Simp 6 we just did was 13.5. TRAP 6, I think I remember a 13.625 or something. You guys will have to correct me on that. All right, has anybody run the RAM? Okay, it's the same equation on your calculator, 0 to 3. LRAM, 12.125. Okay, that was too small. RRAM? 15.125, that was too big. MRAM? 4375, we're getting there. Still too small. And then I think TRAP 6 was 13.625. I don't 100% remember that. And then we have Simp 6 being 13.5. So the progression of accuracy as we're moving through. Simp is almost perfect. Every time, just about, Simp will get it almost exactly right. Okay, Simpson was a smart dude. Okay.
Is this the same guy that made the Simpsons show?
No. Okay, what you have been doing is the Greek letter summa, which we get the word summation or sum from. Okay, summa or summation means to add up. And so you've done 3 kinds of addition. You have been adding rectangles. You have been adding trapezoids. And you have been adding, well, we're letting the calculator do it. Paraboloids. Okay, rectangle, trapezoids, paraboloids. This is called a summation, or where we get the word, our English word, sum, from the Greek letter summa, or the Greek word summa. The Greek letter is called sigma. Okay, you may have heard of sigma, like in different sororities or whatever. Alpha Sigma Pi, Delta Sigma Theta, whatever. Okay. We're good. You can skip that.
Awesome.
Okay. In contemporary, that was what the Greeks used. Okay? In contemporary context, we use this symbol instead. It's an elongated S. So it's a very stretched out S symbol. That is what we use to mean summation. Okay? And it's the symbol that we use for exact area. We know that Simpsons was the best exact area that we had. So this S is kind of for Simpsons. It's also for summa. It's also for sigma. So we use this elongated S symbol. So let me tell you what all these things mean. Okay, this A down here is where you start. The B up here is where you end. The f of x is the function. that you're working with. And the dx is the axis that acts as your lower boundary. We've been doing the x-axis. Will we start doing the y-axis? Yes. Okay, but we're just sticking with the x-axis for now. So what you just found, if we rewrite what you just did, okay, on the one equation that we just did on our calculator over and over and over again, okay, where did we start? We started at 0. Where did we end? We ended at 3. What was the equation? It was x squared, I think, minus x plus 3, and it goes in parentheses. It's not in parentheses, I mark it wrong. Okay, I deduct. And then we put dx because it was relative to the x-axis. And so this says what is the exact area from 0 to 3 of this equation with the x-axis as your boundary. And how would you best answer that question right now? Correct. Okay, so the most exact is going to be that integral symbol. Okay, pause.